Alright, so let us now talk about backpropagation. So when we want to use gradient descent for neural network learning, then we need the gradients. And we need the gradients with respect to our loss function because we want to minimize the loss. For perceptrons, we could easily derive the gradient of the loss function ourselves by hand, so we could just calculate it if we wanted to do that. In general, however, we cannot do that so easily. And how we do that, that is the scope of the Backprop algorithm. And we write E for error or loss instead of F, as we did in the general introduction. Our derivations are based on this book here. There are other derivations and other formulas which are of course equivalent, but they take a different form and a different outline, and if you want to have a look at them, for example, you could watch this video here or many other online resources. So what's the situation that we are facing? Initially, we are in a deep multi-layer perceptron, so these are at some point our input comes in the initial layer, in the first layer the input comes in, and then the input gets propagated through our network, and it has multiple layers, and at the beginning we are at the output layer. So this is now zoom in into the output layer. What we have here is we have our output units with some activation function. The output of some unit j is given by yj, the pre-activation is given by zj, and then we have this matrix w that connects the last layer with the one layer before it, and this layer one before the last layer has of course also outputs activations of its units, and these are we denote by pi. Okay, that's where we are in the network. As I said, this is the activation in the current layer. In our case, it's we initially consider the output layer, then that's a pre-activation, and this is the activation in the previous layer. So backpropagation backprop has two phases: the forward propagation, backward propagation. In the forward propagation, we feed in some. So we are given some input point, xt. X is the representation of the input. T is a vector that represents a label for that input, and we want to compute the gradient at that point xt. Right. So in forward propagation, what we do first is we propagate x forward towards the network, and then on the way we compute all the activations in all the layers, including the pre-activations. Okay. So now we assume, so this is pretty simple to do. This is just linear algebra and some non-linearities put on top of some matrix vector multiplications. Now assume this has been done, and now we focus on the second part, namely backpropagation. So the model situation is we have our loss, and you know the loss is the sum over all these xt pairs, where y is the prediction of our MLP, of our neural network, and we focus on minimizing simply the loss at a given point, at some point xt, and for which y is the corresponding prediction of the neural network, for notational convenience. So we get rid of that sum up here. That is fine. That's like online learning, right? So this here above is like batch learning or mini batch learning. That's like online learning. So you could consider that a special case, but it's not a big issue because it's just a sum here. So the gradient of the sum is the sum of the gradient, so that's not a big deal at all. And we focus on minimizing square loss, but you could in principle substitute other loss functions and derive analogous results, and the square loss is just given by the vector y minus the vector t, taking the norm of that and then squaring that. Good, and how does that look like in individual terms? Well, we sum over all output neurons, j, that are indexed by j. We take tj, tj is the truth value for the unit j, minus yj, we square that, and we can abbreviate that to be a sum over all j's, ej's, yj's, where ej, yj has exactly this definition, right? So this is like an abbreviation of the previous equation. So backpropagation in general is a form of dynamic programming. So you recursively or inductively find a solution for an optimization problem. And in our case, we want to recursively determine the derivative of the loss with respect to the weights. However, initially we have no clue how to do that. How do we come up with a recursive formula that determines the derivative of the loss with respect to the weights? However, we have some gut feeling that maybe we could start out by looking at the following quantity, which we call delta, namely that is del E by del Qi, or dE by dQi. So this means intuitively, how much does my loss or error change when the activation in some neuron, in some layer, namely, well, Qi is just the activation of a neuron in one layer. So when my Qi changes, how much does my loss change? And then once we have found a formula for delta, a recursive formula, then we relate delta to the quantity that we're actually after, and this quantity is dE by dWij, because we want to change all the weights in our neural network, so we have to change any given weight in the neural network, right? Good. So we start by asking ourselves, what is dE by dPi? Where again Pi was well, that is the activation in the previous to last layer, and let's see how that is given. Remember that E, the loss, was just because of the square loss, it was just the sum of these Ej, Yj's. So we have dE by dPi. This is given by the sum over dE j dE pi. Why is that the case? Well, just take the definition of E, and we know that the derivative of the sum is the sum of the derivatives. So we arrive at this formula quite obviously. Then the next step that we can do is we do something that is called the chain rule, and we say, okay, let's rewrite this term dE by dPi as a product of two partial derivatives given by dEj by dyj multiplied by dyj by dPi. Okay, and what is yj? Well, that was the activation function. That was the activation of the jth output unit. And if you don't recall this formula, there's some hint that you can use, or some some guideline, like informal guideline that you can use to always remember the formula. You just pretend you could calculate like in elementary school, so you could cross out these two factors and you will get what you had before. Okay, so this is like an informal manner of remembering this formula. So that's the chain rule. And now remember that dEj by dyj, that is given by d capital E by dyj, because this E function is a sum of these little E functions, of these little E terms. So if we take the derivative of this big e term by dyj, well, yj appears exactly only once, so all the other ones cross out and only this one remains, right? So we have this identity here. So what we can do by this identity, well, we plug that identity in here. So okay, now that already looks quite good. So how do we continue now? Now we know that yj, the activation in the jth output unit, is just the pre-activation and the nonlinearity plugged on top of the pre-activation. Good, therefore we can calculate this quantity here quite easily. That's the chain rule. Again, so we take outer derivative times inner derivative, right? So, and then set j, well, this was just, set j is the pre-activation of the jth output unit. So this is just given by, well, it's given by the vector of activations in the previous layer. It's given by the vector of activations in the previous layer, just similar to how we calculated the pre-activation in a perceptron. So we take the input, so to speak, and the input is the activation of the previous layer, multiplied by this weight vector wj, right? So if we then want to calculate this set j by dpi, then well, we only have here, that's just a summation, right? So you could split that summation up into the individual components, and what we get is just, we get the ith component here, right? Because if you, well, this is pi times wji summed over all I, and if we do if then we do the derivative by pi, we only get the only thing that remains is the coefficient of pi, and this is wji. And wj is a vector, and we take the ith component of that vector. Then when we look at this in terms of a matrix, we get of the matrix W exactly the element Wij. Okay, and this is because W is given by these column vectors W1, W2, W3. So we have the column vectors, and Ij, so this is the ith component here and the jth component here. This is exactly the same as taking the jth vector and the ith unit of that, because these are column vectors. Okay. So we have three ingredients. So we have this one here. This already looks like a recursive formula, right? And the next term here is because we have DEPI expressed as the sum of DE YJ. So that's already a recursive formula. Then this term here, to calculate this, is quite easy. When we do that, we get such a formula again by the chain rule. And then this last term here is also calculated quite easily. So plugging these three things together, we get the formula down here. dE by dPi is given as a sum over all j's. Then we get this term here, and this term from here, and this term, right? Cool. So what is the result? What does that mean? So we express the error derivative, dE by dPi, in the previous layer in terms of the current layer. The current layer is the final layer, right? dE by dyj. Cool, that's a great result. We already know what the error derivative with respect to the last layer is, namely this is dE by dyj, so we can just calculate that. How do we calculate this? Well, dE, this is the formula, and then ej yj is given here, right? This is also this formula. Now we just take the derivative of this formula. So we can just find the solution for that. So this is like the base case. If we're in induction, right? That's the base case. We know the derivative in the last layer, and from this we know the values at the layer before the last layer. So we know these values. We know the current weight values. We also know them. We know these. We know the pre-activation set J, right? Because that we got from the forward pass. And the forward pass, we compute all the activations. We also know the non-linearity function. So these are just functions like tanh, sigmoid, or something else, and we can compute their derivatives. So we can also evaluate these derivatives at these individual points. So we know everything here, so we can compute dE by dPi, right? Cool. But if we know that, then we can just apply our formula again. So now we derived everything by saying we are in this last layer, in the last and previous to last layer, but it actually applies to all and any of the layers in the network, right? So we can, because I mean, that was just for our visualization, but the mathematical derivative did really not depend on us being in the last layer, right? So we can apply our formula again, and we get the same conclusion, dE by dPi, where Pi is now an activation one layer before the layer that is one before the last layer, and we can again express it in terms of the dE dyj, where yj is now the layer after that layer, right? So that means in general we can backpropagate the error derivatives from the last layer to the very first layer, and we can compute all these values dE by dPi throughout our network. Okay, cool thing. However, now we're not looking for these dE by dEPIs, but we're instead looking for the derivatives of the loss function with respect to our weights duik for all the weight matrices U, right? From the first to all the weight matrices that we have in our MLP. However, fortunately, we have the following relation. dE by duik is given by dE, the derivative dE by dmk, multiplied by sigma prime zk multiplied by Li. And what are these terms now? Well, dE dmk, that is one of the quantities that we have recursively computed up here, right? That's one of those quantities. Sigma prime, that's again, this is just the derivative of the activation function. Zk, this is some pre-activation. This is the pre-activation of mk. And Li, this is the input for that layer. Well, like L takes the role of P previously. Okay, so no matter where we are, in which layer and in which unit in that layer, we can express the derivative of the loss function with respect to that particular weight in such a form, right? And this is what you can do yourself just by like doing some mathematical manipulation. It's like, you see, like we have the first equation. This is again some chain rule, and the second one is also a chain rule, and some simple mathematical operations like taking this identity into account here. Okay, and just for illustration, like li is what was previously had the role of pi, except that this li is in not the the last layer, the previous to last layer. However, now li is in some arbitrary layer, right? And then we have u that's connecting this arbitrary layer with the next one. Zk is the pre-activation, mk is the activation. And here's very simply and very briefly the math to it, even though we will not go much into detail. So u consists of these column vectors u1, uk, uik is that weight here, and that's the chain rule. And this this here is again the chain rule, and then this by this dzk by duik, that was that weight here, is just given by li, because we have this formula here. This is very similar to what we have seen previously, or this actually completely identical to what we've seen previously. This was the equivalent of this formula here, right? Good. So what we have is we can plug everything together. We know how to get these error derivatives with respect to the activation functions, but we know how to get them recursively with backpropagation, even though we do not directly want this quantity here, but instead we want to have the derivative of the error function, the loss function, with respect to the individual weights. However, we know how the loss function with respect to the weights is connected to the derivatives of the loss function with respect to the activations. And so we know that this identity here holds. This is what we get from backpropagation. This is what we get from forward propagation. This is the pre-activation, and this is some activation. We get this in the first part of the backpropagation algorithm, in the forward propagation step. And we know what is the derivative of the loss function, because we know what form the loss function has, so we can always calculate its derivative. And this concludes the backpropagation algorithm. So what the backpropagation algorithm is, it's a recursive algorithm for determining error derivatives. It starts at the outer layer, at the last layer, at the final layer. It propagates the error derivative signal backwards by expressing derivatives in one layer in terms of the next layer derivatives using the chain rule. So we're using the chain rule here. And note that it may be note that this is a general technique for calculating derivatives of composite functions. Modifications apply also to other mathematical objects, not only to multilayer perceptrons. All right, let's look at some example of backprop. A very brief example, which you will also discuss in the tutorial. So let's say we have this this network here. It has 3 input units U1 and 3 input units. The second layer has 1 unit. The third layer has 2 units and then 1 output unit. And we have these connecting weights here, U, V, and W. And assume all the activation functions are 10H, and the loss is square loss. So let's say we initialize our network randomly. We take some random values for U. They are given, let's say they are given by 0.2, 0.5, -1. Some random values for V. Some random values for W. Assume that our input is 1, 0, 1, and assume that for this this input the true value is 1. The prediction should be 1 for that unit. And we have the square loss, which is t minus y squared. We first perform a forward pass, so we feed x into our model and compute everything from the activations to the loss. Also, we can compute the loss. Now we switch to the backward pass. So this is very easy to calculate, right? It's just like very simple mathematical operations. Then we switch to the backward pass, and we compute our DEs by DPIs, and these are the values. If you do the backward pass here, then these are the values given, and you can check that in the tutorial, how you can go through that in the tutorial, how whether these numbers are actually true. And I think there may be a few errors in the calculations that we have made. Maybe there are a few rounding errors or a few more serious errors, but you'll check that exactly in the tutorial. And once we have calculated these numbers here, then we can calculate the derivative of the loss with respect to all the weights given by the formula that we have previously outlined. For example, if we want to calculate the derivative of the loss function with respect to u3, so u3 is here, then we would consider dmk, so that is that value up here because it's the next layer. So this is minus 0.12 times sigma of zk, which is well, that's the zk is here, I guess, and if we plug in zk, which has some number, into sigma prime, we get 0.55 times li would be this third number here, because that's number 3. So yeah, so we're connecting, u3 connects the third input with the next hidden layer. So in total the value would be, if all these calculations are indeed correct, minus 0.61. And how can we do a gradient check? Can we check that numerically, whether it's true? We can check that numerically by doing the following. We can do a numeric approximation. Recall the formula for the derivative f prime of x in general for any arbitrary f is defined as fx plus h. So from the point x we go a little bit towards the right, minus f of x, and then we divide, or to the right or to the left, right? Minus the value at the point x and divided by h. And then in mathematics you let h go to 0, but as a numeric approximation you can just make h very small. And then to check whether the formula for dE by du prime is correct, what we can do is we compute our loss E at the value at u prime, where u prime is given by well, that's the original u. The original u is given up here in the last unit, because we want to have the gradient with respect to u3. We add an h, we keep everything else the same, and we also compute the loss at u when the weights have the original values, and we plug all of that into our error function or loss function. So we plug in x t u prime v w and subtract from that the value of E at x t u v and w, divide by h. So this is the formula given up here. And then if we let h go to 0, or on a computer if we just make x quite small, then what we get is we get a numerical approximation of the exact gradient dE by dE by du3. Okay, and so this is, you can always make such a numeric check whether you have done everything correctly in your calculations. And so what is the drawback of that formula? Well, the drawback of that formula is in the backpropagation, we are actually getting it cheap, because we could always do that numerically. So there are two things that speak against this using this formula. The first one is, well, it's just an approximation. It has maybe numerical instability, so you divide by something that's close to zero. Maybe that's not so good on the computer. The other thing that is a drawback is, well, here you have to do 2 forward passes, right? So to calculate this value, you have to make one forward pass here, another forward pass here, and then divide by h. So that's not costly, but 2 forward passes. And we would have to do that for each unit, for each weight in our network, right? For each weight we have to make 2 forward passes, while the back propagation in general just makes 1 forward pass and 1 backward pass. So that's much cheaper, right? Okay, so now let's talk in the next part, in the final part of this part of the course, of this lecture. Let's talk about language models, and in particular neural language models. And we talk about them because they have become, so they are, first, they are a very old tool that has been around for a very long time, and secondly, they have become very popular again with Elmo and Bird and everything. So language models have seen a big revision or a big revival in NLP, so we talk about them here, and they are basic building blocks of modern NLP. So what is a language model? A language model is a model that assigns a sequence of tokens, which could be a sequence of words or characters, a probability. And this probability denotes the likelihood of observing this sequence in the text. And intuitively, what we want is, we want the probability of a sequence like the cat sat on the mat to be higher than the probability of, let's say, some random permutation of these words. What are use cases of language models? First use case is, let's assume you're doing machine translation, and your machine translation system translates from English to German, so you get an English input, it generates you a German translation. Let's assume you have 10 such translations, and let's assume your system gives you 10 translations. Then we could score each of these translations by a German language model, which says which of those sequences is actually the most well-formed and the best of these sequences. And the other other very popular use case of language models is for generating text, and that's why they have become popular again in recent years, because generating text is a cool application, and not only because of that, but that's also one very cool use case of language models. So let's do, because we have talked about probabilities, let's do one slide primer on probability. Of course, if you do that in a math course, it will be much more rigorous and much more exact, so we just do the most basic introduction that you can think of. So what is the joint probability? You have two events A and B, like these are also these are sets. So you have two sets A and B, which we will call in the terminology of probability as events. So what's the joint probability of A and B? Well, we don't know yet what it is, but we also denote it in different ways. So one of them is we just use a comma. What's the joint probability A comma B? So this is an intersection symbol, or we just like do nothing, we just make an empty space between A and B. And the meaning of this, the probability of A and B is how likely, the intuitive meaning of that is how likely is it to observe the events A and B jointly, right? Then besides the joint probability, there's also conditional probability, how likely, which means how likely is it to observe A given B. And there's also the marginal probability, PA, how likely is it to observe simply the event A. Well, that's called a marginal probability in contrast to a joint probability, just like you focus on one of the two events. Now let's look at some space of possible events. So like we have 1, 2, 3, 4, 5, 6 objects, in this case 6 humans, and so some of them are females. The red ones are the females, the blue ones are the males, and some of them committed a crime and others did not commit a crime. So let's do our let's calculate some probability. So what is the probability that in this space someone is a female? So we count all the females, so we have 3 females over 6 people in total. So in this space the probability is 1/2. What is the probability that somebody is a female and also and in addition committed a crime, right? So this is the joint probability of these 2 events occurring jointly, and let's look at that. So we have 2 females that committed a crime. So we have two objects that are both female and committed a crime among a total of 6 objects. So it's 2 over 6. So what is the probability that if someone committed a crime, given that someone committed a crime, that this person is female? Let's compute that. So if we are just focusing on those people, those objects that committed a crime, we have these 3 here, and out of these 3, 2 are females. What is the reverse probability of somebody committing a crime given that they are female? What do we have to look at here? Well, we have to look at these things here. All the females are the red ones. How many of those committed a crime? So it's again 2 over 3. What in this space is the probability that somebody, given that somebody is male, that this person will commit a crime? So we have all the males in blue here, and that they commit a crime. Well, that's 1/3, right? Okay, so this was the 1 slide primer on probability. So now let's look into n-gram language models. So in former times, before neural networks became the standard, a common approach to language model was to use so-called n-gram language models. And what they do is they approximate the true probability P of a stream of tokens. So we have what is the true joint probability of a stream of tokens W1, W2, W3, W4. We can express this true joint probability as a product of conditional probability. So this is the conditional probability. And this product is given by this formula here. And this formula is very easy to remember if you just if you look at the definition of of joint probability and conditional probability, because the definition of conditional probability is the following. All right, let's verify the let's verify this formula for the joint probability of a sequence of words W1 or sequence of tokens W1, W2, W3, W4. So this is the formula, this is the identity that holds for this joint probability. We can rewrite this joint probability as a product of conditional probabilities. And why does that hold? That holds because the definition of the conditional probability is given here. It is a joint probability divided by a marginal probability. Let us verify this by way of example. If we look at this example, at our previous example of what's the probability that somebody commits a crime given that he's male in our little world, then we said, okay, we check all the males here. These are 3 guys. One of them has committed a crime, so the probability is 1/3. We can do this also by first going for the joint probability that somebody is male and doing a crime. So this is exactly 1 case here out of 6. So this is 1 out of 6 divided by the probability that somebody is male. This is 1/2 in our little world. So 1/6 divided by 1/2 is 1/3. So that was correct. So if we have that definition of joint probability, then that we can calculate out the individual factors here. We do the first factor times the second factor. Then we find that this equals the joint probability of P1 times P1 and P2. So this factor here is the joint probability of P1 and P2. multiplied by this term here gives the joint probability of P1 and P2 and P3 and so on. So we can calculate this, and in the end the equation here is the identity here is satisfied. So now this is the true probability. The true joint probability can be written as a product of conditional probabilities, and an n-gram model makes the approximating assumption that all of these conditional probabilities are clipped to a history of n words or n minus 1 words. So that means here we have the history of 4 words, but if we have a bigram, or let's say if we have a trigram model, then that would be clipped to the 2 words, to those 2 words here, right? So it would be clipped to a history of the previous 2 words, and this one here also would be clipped to the history of the previous 2 words. This one here also, but here it's already the identity. This also would be clipped, but it doesn't change anything because the history has size 1 anyway, and the same is true for this. So if we make it by example, then a 1-gram language model approximates the true joint probability of all of this sequence of tokens by the marginal probability of each token, right? Because a unigram language model takes a history of size 0 into account, and if we have a size 0 history, then all these conditional probabilities here they drop just to become unconditional probabilities. And in the Bikram model, a Bikram language model would approximate the probability of a sequence of tokens as a conditional probability, as a product of conditional probabilities, where each term is given by the probability of the current word given the previous word, except for the first term, which has a history, which anyway does not have any history, so we cannot clip anything, right? So this is an n-gram language model. And how are n-gram language models traditionally estimated? So the estimation of these conditional probability that conditions on the n minus 1 previous words is given by first applying the definition of conditional probability, namely that it is a joint probability divided by a marginal probability, and then these joint probabilities are just given by are estimated by counting the respective sequences of tokens. So if we would estimate what is the probability that dog follows the, we would count, this is not an equality sign but a approximation sign. We would count the occurrences of the dog in our corpus, so we have a corpus of text. We would count the occurrences of the dog and divide by the occurrences of the. So this is the approximation of this, or this is the estimation of these conditional probabilities. And in addition, some smoothing is usually performed to account for words not seen in the data. So the idea of smoothing is we should not assign 0 probability to anything. So instead of assigning 0 probability, we could add some real number or some integer up here and also some integer up here, so that 0 never occurs, because we don't want to have the value 0, because because if we have 0 anywhere there, then if any of these factors is 0, then the whole thing is 0. But setting something to 0 is not a good thing, because any corpus is just a finite amount of text, and there's always something that will not be encountered in the corpus, but has a a positive probability if the corpus were bigger, right? So and therefore we want to account for this this fact that our corpus can only represent a specific domain of language or a specific aspect of language, while the reality the reality is still not exactly captured by our corpus. Okay, and in particular, to illustrate this with a concrete example, so you would not want to assign zero probability to the string the dog, um, especially when maybe you have seen a dog and a cat in the data, right? Then this illustrates you why it would not make sense to set this to zero. Okay, so this is how n-gram language models can be estimated from data. We can also implement an n-gram language model with a multi-layer perceptron, not using such count estimates, but using a different approach. How would that look like? This is one of the earliest neural language models proposed by the group of Joshua Benjo. How did that work? This network here computes it computes a 4-gram language model, so the history is of size 3. So each word is conditioned on the previous 3 words. So what is coming into this neural network is the previous 3 words. In this case, these words are represented by an input vector of size 3, a one-hot vector that just gives the index of this word. So this vector would say cat is the first word in the vocabulary, on is the second word, there is the third word. And keep in mind that this is just an accident, that this is a 4-gram language model and the vocabulary has size 3. So this is not, there's no connection between that. Our vocabulary could have size 1000, then this vector would be of size 1000, this vector would be of size 1000, and this vector would also be of size 1000. Okay, so we feed our history into our neural network. Here are like connecting matrices. Here's a connecting matrix. Here's the 10H activation function. Here's another hidden matrix, another weight matrix, and in the end we have a softmax activation function for the final layer. And here this is a little bit confusingly portrait. So this is pretending the softmax is applied to these neurons, and then and then there are other neurons here, but actually it's just, this is the final layer and the softmax is there on the final layer, so that whatever is coming out of the final layer is a probability distribution. So our probability distribution would exactly encode this part of the, or like this equation of the 4-gram language model, namely the probability that a word, the next word is cat, given that the previous 3 words were cat on the, is 80%. The probability that the next word is on, given the history, is 50%, and the probability that the next word is the is 5%, given this history, right? So that's what the 4-gram language model is computing. Now, if we had a 3-gram language model, it would just look like this, right? We would have one input less, and if it were a bigram language model, we would have another input less, right? And now, what is the difference of this model and the previous MLP that we have seen? Well, there's only one difference, and this one difference is that we do not have an independent matrix that connects the input with the first hidden layer, but like so there's no full connection between the first layer and the second layer. So in a standard MLP, there would be this would be fully connected, but here it's not fully connected. So this input is only connected with this part of the network, and this input is only connected with this part of the network. And also there's weight sharing. So all the way, so um, this matrix here is copied 3 times, right? So this means that this weight is the same as this weight, and it's the same as this weight, and this weight is the same as this weight, and the same as this weight. Um, and why is this the case? So the idea is what we've seen already in the first lecture, very briefly on a high level, that we're doing an embedding. So the one-hot vectors, which are just indices, this is the first word, are embedded into real numbers. So we get this one-hot vector multiplied by this matrix, just gives the one row of the matrix, and this row of the matrix is a vector of real numbers, and this is exactly this activation here. And the idea would be that similar words like cat and dog would have similar representations here, right? And this is hopefully achieved by this assign. So if you train this model long enough, then hopefully you get out a matrix E that has exactly this property, that similar words, intuitively similar words, have similar representations when the index of the words is multiplied with this matrix here. Okay, so the first thing that we can do with language models, that's what I've discussed before, is we can score strings with them. How do we score strings or sequences with language models? Well, this is very simple. If we have a language model, let's say an n-gram language model, we know what the joint probability looks like, and this joint probability can be written as a sequence of conditional probabilities, and we know what how the conditional probabilities are how they are approximated by an n-gram language model, namely in this way. So we plug in all these these n-gram approximations into our formula, and we multiply all of these factors, and then if we do that, we get a score for the whole sequence, right? And then we can evaluate all kinds of sequences, whether they are meaningful, whether they are likely to occur in any particular language that we are dealing with. Good. So this is the first thing. The second thing is we can generate language with a language model. And how would we generate language with a language model? Let's see this by illustration. We want to generate language with a bigram language model. How would we do that? Well, we look at the probability, at the unigram probability of any word. So this unigram probability is part of any language model because it always starts with the first word conditioned on nothing, right? So we sample a word from the unigram probability, and this unigram probability could be given by counting, or it could be given by such a neural network without any inputs, right? So we sample. So let's say in our corpus, the probability to sample the word cat is like 30%. Okay, so with 30% we sample the word cat, and let's say in our corpus the probability of sampling the word dog is 10%. So with 10% we sample the word dog. So we start with cat or dog here with either of these two probabilities. Once we have sampled, let's say we have sampled cat. So now we know that this word here is cat. Then we sample from the conditional probability that of the second word given the first word being cat. So if this were a bigram language model, this part would drop out. So we would feed in cat here, we would get a probability distribution out, and then we would sample these words with their respective probability. So in this case, cat would have 80% of being sampled, on would have 15%, and so on, right? And then we can successfully do that. So we sample the next word, plug it into our Backprop language model, and from this part we sample the next word, and so on until we generate a really long sentence. Now the problem with n-gram language models, so this is how they can be used for language generation. The problem with n-gram language models is that they are inherently limited in the past window that they can take into consideration, because they can always only take a fixed amount of n previous words into consideration. And this is of course not a good property for language, because imagine you start a paragraph with you have a quotation and which is given in a paragraph, and you start with an opening quotation mark, and then you generate 500 words and you want to close the quotation mark, then the n-gram language model would be unable to explain why you should close the quotation mark, because the n-gram language model can maybe only take a history of 10 words into account, so it cannot look back into what has happened like 500 words ago. So what is much better than n-gram language model is an RNN language model. And we have already seen recurrent neural networks. These are these multi-layer perceptrons that have this recurrent connection that feeds one hidden layer from the previous hidden layer, right? So we have a hidden connection between the current hidden layer and the previous hidden layer, and this allows us to, when we make a decision up here, that allows us to take into account all of the previous inputs and all of the previous words, right? And in that way, we can really calculate the exact probability as given here by this. So we can calculate the exact conditional probabilities for each of these factors, right? We can really condition on a history that is arbitrarily long. And how would that be implemented in practice? So in practice, such an RNN would be at train time. It would be would be forced to predict the next word. So if the input if that is the input, then at each time step it would be forced to predict the next word. What is the problem, right? So it would be predict to solve such a problem. And in this case, at each point in time, as I said, and here would be a softmax. So at each output time step would have a softmax activation function, and this gives a probability, and this probability can really be interpreted as what is the probability of this word here given all of the previous input words, right? Mediated over these hidden layers, right? That's the interpretation that we give to this softmax here, and this softmax, and this softmax also. So there's no n-gram approximation. And at generation time, at test time, so to speak, once we have trained the model, we sample from the softmax and feed it into the next time step. It looks like this here. If now assume we have trained the model and now we would run it with the initial word like what. We would feed it in. It would predict some activation given by softmax in the output layer, and we would sample from that softmax. Let's say we sample is, because that has the highest probability here, but we could also sample the first word, whatever the first word in the vocabulary is, right? Just with lower probability we would sample. Once it has been sampled, we feed it into the RNN as input in the second time step, right? And then again we do the same. We get a softmax here, and this softmax would be considered as the conditional probability of each of these words in the vocabulary given the history of the previous two words, and we would sample again one of the words and feed it into here, right? And if we wanted to know what is the conditional probability of the given what is, we would go to the index of the word the in our output vector, right? In our output vector corresponding to the output layer. Okay, and a final note, I mean, it is common to pad the input with a SOS, start of sentence symbol, and predict an end of sentence symbol in the last time step. Why would we do that? Because if we do it like this, if we start from some concrete word, we would always have to give the neural network, when it's generating something, would always have to give that network some initial input. But we want to start generating without any given input word, but just by itself, so to speak, right? And therefore we would say we would start out from the start of sentence symbol, and then it would say what is the actual first word in my sentence. We would generate that actual first word, then we would generate the second word in the sentence, and so on. And we would stop generating when the model predicts the EOS symbol. So at each time step it would predict EOS with a certain probability. That probability could be very close to 0, but in any case the EOS symbol is in the vocabulary vector. It would predict it with some probability, and at one point in time EOS gets sampled, and at that time point we stop generating, and we know that our sentence is finished. Good. So this is a very brief glimpse into language models. They have seen a real revival in NLP because of a couple of factors. One of them is, for example, they can be seen as cheap auxiliary tasks. So in the first lecture we have briefly seen multitask learning, and there I said, well, the idea is to solve multiple tasks at the same time, and then language modeling is a very cheap auxiliary task. So you solve some main task, whatever that could be. It could be part of speech tagging, for example. You solve that main task, and then you always have labels for the auxiliary task, that is language modeling. And because your sentences always have for each word in the sentence, there's always the next word that can be predicted. So this is a auxiliary task that we get for free. And what, for example, Marek Rai has shown is that if you add this auxiliary task to any or to those NLP tasks that he has investigated, then actually the NLP tasks can be solved with a higher accuracy, right, with a better performance score. So this is a cool thing. But mostly language models have become so popular because of these contextualized word embedding models. Initially it was Elmo, which was computing a language model objective, predicting the next word, and it got these contextualized representations from the language model. But then also, like all of the current very high performing architectures, especially BERT, they also do this language modeling. They also solve this language modeling task. So in BERT it's a little bit different. It uses masked language model, so it's not language modeling. It's not this ordinary language modeling, and it's also bidirectional. We only see unidirectional, but in essence, it's also doing language modeling. And the cool thing about language modeling is really that you have to predict a future word in the text, or some word that is absent from the text. And what the last 3 years have shown, if you can do this really well, you can get really good representations of text data of either words or sentences or something. And that is why language models have become so popular again, even though they are very old technique and have been investigated for a long time and were not so important in NLP in the last couple of years than they have become in the very recent past. Okay, so we conclude this lecture. Lecture number 3, we saw gradient descent, which is a general technique for optimization. And we saw some extensions of vanilla gradient descent. We saw stochastic gradient descent, which is also called on-line learning, mini-batch learning. And we've glimpsed into possible other extensions like Adam optimizer or second-order methods. The core thing about gradient descent is that it is optimizing any particular function which is differentiable. It is optimizing such a function, and in our case we always did minimization, so it's minimizing functions, and it is minimizing functions by in particular taking only the gradient into account, which makes it a cheap method that is guaranteed to perform well in certain contexts. At least if there's a local minimum, it will find this local minimum if the function is differentiable. So that's the first very general technique from a nonlinear optimization that we saw. Then this very general technique requires the gradient. Where did we get the gradient from? We got the gradient from backpropagation. This was a general technique for deriving the gradients in multilayer perceptrons, and maybe some and other neural network architectures, and maybe also beyond. So we could get the gradient there. Once we have the gradient, we can plug the gradient into gradient descent and use the combination of these two approaches to train our neural networks, to learn our neural networks, to minimize an error function. And this error function says the neural networks should, their predictions should be close to the training examples that we give them, right? And so this is the error function that we minimize, and we minimize them by the combination of backprop and gradient descent. After that, so this was general deep learning and general optimization. After that, we came to language models, and there we saw n-gram language models. First, we saw the definition of a language model, then we saw the n-gram approximation, and we saw an RNN language model that does not make this approximation, and thus is more exact and much better in modeling language. And this concludes lecture number 3.